Current transformers are the vital sensory organs of the electrical grid. They step down massive transmission line currents into manageable signals for relays and meters. When a CT fails, it blinds the grid's protection logic, allowing faults to propagate unmitigated. Commissioning these units involves navigating overlapping international standards from the IEC, IEEE, and ANSI. To resolve conflicts between codes, specialists adhere to a single governing rule: always apply the most stringent approved requirement. The procedures we follow are dictated by a specific physical hazard. A CT is essentially a step-up voltage transformer operating in reverse. If you open the secondary circuit while the primary is under load, the opposing secondary ampere turns drop to zero. The magnetic flux inside the core immediately surges, inducing a theoretically infinite voltage across those open terminals. That unchecked voltage rise rapidly exceeds the equipment's dielectric limits. The insulation breaks down, resulting in catastrophic failure and lethal arcing for anyone nearby. To verify internal integrity before energization, field engineers rely on two primary diagnostic tools: a 5 kV DC insulation resistance tester, commonly a Megger, and the Omicron CPC100 multifunctional test node. Because of the open secondary hazard, testing never begins without isolation. The protocol requires 5 distinct safety steps: applying safety tags, isolating the area, maintaining safe distances, wearing appropriate PPE, and implementing proper protective earthbounds. Every procedural hold point and secondary shorting step in the commissioning matrix exists specifically to mitigate the physics of an open circuit voltage spike. The testing sequence begins with insulation verification. This process maps the safe dielectric boundaries of the CT, ensuring no leakage paths exist between the windings and the chassis. The first connection targets the primary to ground boundary. The Megger is connected between the primary terminal H1 and ground, applying 1000 volts of DC for exactly 60 seconds to measure baseline resistance. Next, the leads are shifted to test the primary to secondary boundary. The voltage is reduced to 500 volts DC, verifying isolation between the high voltage input and the sensitive relay outputs. Finally, the secondary to ground boundary is tested, again at 500 volts DC, confirming the secondary wiring is fully isolated from the chassis earth. These tests charge the transformer's internal capacitance. The technician must hold the measurement until the resistance readings stabilize, and then actively discharge the system after every test to neutralize stored energy. Once the insulation is proven sound, we move to the turns ratio test. Here, we measure the physical electromagnetic behavior by injecting a known primary current and verifying the exact secondary output. The Omicron CPC100 drives current through the primary H1 and H2 terminals. Simultaneously, its voltage sense leads monitor the resulting output across the secondary X1 and X2 terminals. Inside the software, the technician enters the expected nameplate parameters directly into the CTR ratio test card, giving the instrument a benchmark for its pass-fail logic. The CPC100 can directly inject up to 800 amps. For substations requiring primary currents above that threshold, an external current booster is integrated into the loop. Verifying both the insulation integrity and the exact transformation ratios guarantees the protection relays will receive accurate, uncorrupted data during live operations. We then advance to the excitation and kneepoint determination test. The goal is to map the magnetic saturation limits of the CT core to confirm it is suitable for its designated protection class. This test is run in reverse. The CPC100 operates by driving an AC voltage into the secondary circuit at X1 and X2, while recording the exciting current, keeping the primary circuit completely open. This screen output graph displays the resulting excitation curve. Following the IEC 600441 standard, the system identifies the exact knee point on the logarithmic curve, the specific coordinate where a 10% increase in applied voltage results in a 50% spike in exciting current. Alternatively, the IEEE standard defines saturation differently, pinpointing the exact spot where the tangent line to the curve forms a 45-degree angle. After determining saturation, we measure the winding resistance to evaluate the physical integrity of the secondary copper coils. The instrument applies a DC current via Kelvin leads directly into the secondary terminal block, measuring the voltage drop to calculate absolute resistance. Raw DC resistance data taken in the field is problematic. Copper resistance fluctuates heavily with ambient temperature changes, meaning a measurement taken in extreme heat will differ drastically from one taken in the cold. This interface shows the solution. The CPC-100 applies the IEC 60076-1 temperature compensation formula, automatically normalizing the field resistance values to a standard baseline temperature for accurate comparison. This procedure carries a severe safety warning. Never break a measuring circuit while DC current is actively flowing through the winding. The inductive kickback will generate a lethal voltage transient. Technicians are strictly instructed to wait until the instrument finishes its automated discharge cycle and the warning lights extinguish before disconnecting any leads. By combining the core's magnetic saturation map with its thermally compensated resistance, engineers can accurately predict how the CT and the downstream relay will interact during extreme fault currents. Next is the high-voltage dielectric withstand test. Here, the secondary insulation is subjected to the maximum electrical stress it is rated to survive. During this procedure, the secondary terminals will actively carry lethal AC test voltages reaching up to 2 kilovolts. Before initiating the sequence, technicians must establish a strict physical exclusion zone around the testing boundary and implement direct communication controls. The CPC-100 is programmed to carefully ramp the voltage up to the target threshold, hold it for the specified time span, and then ramp it down continuously to 0. Throughout the hold phase, the operator monitors the unit for any signs of insulation breakdown, arc flashover, or asymmetrical leakage currents that indicate a compromised dielectric boundary. We conclude the active testing phase with polarity and core direction. Physical integrity is useless if the secondary signal is flowing in the wrong logical direction. To verify orientation, the CPC-100 injects a specialized asymmetrical sawtooth signal directly into the primary H1 path. To conserve power, this signal is applied on an intermittent duty cycle. The instrument pulses the signal for 2 seconds, pauses for 9 seconds, and repeats. Out at the secondary terminal block, the field technician uses a handheld CPOL polarity checker. This device reads the waveform signature of that asymmetrical pulse. If the checker flashes a green LED, the polarity matches the engineering design. A red LED indicates the signal path is inverted or heavily distorted. If a red LED is detected, protocol requires the operator to entirely power off the test set before attempting to disconnect or swap any field terminals. An inverted CT polarity will cause differential relays to miscalculate power flow, leading to immediate misoperation. Directional logic verification is the grid's final defense against false tripping. With the primary tests concluded, the focus shifts to data analysis. Commissioning specialists must know how to interpret specific testing anomalies in the field. If the winding resistance values are abnormally high, or the turns ratio shows massive erratic deviations, it is the primary indicator of an unintended open circuit within the secondary wiring. The immediate resolution is to halt testing entirely and physically reinspect all shorting links, burden connections, and tap wiring for faults or loose landings. If the excitation curve returns an unexpectedly low knee point, the core is entering magnetic saturation far too early. This strongly suggests a shorted turn deep within the secondary coil, or that the technician is testing the wrong metering core. If the high-voltage withstand test trips the instrument prematurely, specialists check the terminal box for moisture ingress or carbon tracking before condemning the internal insulation. The manual ends on the single most critical hold point in the commissioning process. Never leave a current transformer secondary in an unsafe state. Before the permit is cleared, a designated witness must confirm that burden cables are relanded, shorting bars are correctly configured, and terminal covers tightly secured. The procedures, test equipment, and diagnostic data all serve a single objective. The commissioning process is complete only when the physical as-left field conditions perfectly match the engineered grid protection design.